Okay, so in this video, I want to introduce to you something called the simplex method. One of the first things I want to warn you is don't be fooled by the name. It is by no means simple. However, I don't want to scare you, right? It's doable. As a matter of fact, I'll explain to you what you're expected to do when it comes to using the simplex method to solve those maximization or minimization problems in the programming. Now, um, what's wrong with the graphical approach? Graphical approach, right? And you remember that. What did it involve? You had a set of inequalities, x plus y is less than 10, 2x plus y is less than 110. All these x is greater or equal to 0, y is greater or equal to 0. So we have these, and what you do, you normally plot some graphs, you pick out a feasible region, this region here. You take each one of these points, and if you have an optimization or what you call an objective function, sorry, I say p equal to 10x plus 15y. You take each of these points and you substitute it in here and you look for, well, depending on what you want. You want a maximum value for p or a minimum value for p. What is wrong, or not what is wrong, the limitation of the graphical approach is that if we have a third unknown, let's say you have x plus y plus z is less than or equal to 10. With this third unknown here, again, here you have 2x plus y minus z is less than or equal to, let's say, 20. But you have that third unknown. What would happen? These here, if you want to try to graph x plus y plus z equal to 10, and 2x plus y minus z equal to 20. If you were to try to graph these are not lines anymore, they're planes. And you will now end up working in three dimension and not two anymore. And picking out the feasible region and the vortices, and so they'll not be that easy, right? And therefore, that's a limitation of this graphical approach. And therefore, there was a search for a new method, right, that we can use to solve linear programming problems that will have three or more, because you have 4, 5, 6, 7. You can have a lot of unknowns. You know, the real world problems don't often have just two unknowns, right? You might have several of them, and therefore it will require quite a bit of camera, especially when you go on over the four. How you visualize? I mean, when you got three unknowns, you got 3D or three dimensions. When you got four, how do we graph that? We can't graph it, right? You have no way to mathematically, slash geometrically to represent four dimensions, right? Therefore, we had to find a new way of solving those problems that are more complex. And there was born, right? There was born the simplex method, right? The simplex method. And I'll tell you up front, because this is the starting video. Before when you see what I'm going to do next, it's no short of mathematics. You want to know what am I doing? You hardly understand what I'm doing. And to follow the procedure is not easy. It's not easy. It's a complex procedure. But what I want you to what I want to tell you from the outset is this: search for a simplex calculator, so you don't have to do the process. What you may have to do is you may have to form the inequality, right? And you may just have to enter the coefficients into a simplex calculator, right? And you press calculate, and the simplex calculator will do it for you, right? We're not living in a primitive world. You have computer programs that do everything, almost, right? So I tell you that from the outset, but I'm still going to show you the procedure, uh, that you can do by hand, which I strongly advise against doing any simplex calculation by hand, unless it's very, very simple. Like the one I'm going to show you, I choose a very simple one, right? So it's going to be easy for me to do. But when especially when it gets, and I'll do one where you have a third unknown. So I'll have one where you have X, Y, and Z. And you will see how complicated that one. And as soon as you see that one, you're going to go and find a simplex calculator to use, right? So what really is the method, right? It's a matrix approach. That's why matrix came before this. It's a matrix approach. The only thing is that the course has so limited amount of time, right? There's a procedure in matrix. We call them row operations, right? And what you might not know is that when you have a matrix, swap a matrix here. When you have a matrix, let's say you have 2, 1, 2, 3, 2, 1, 1, 2, 3, like this here. Row operations mean that you could do anything to this row, right? You could not anything, sorry, but you can divide this row throughout by 2. You can divide it by 4. You can add this row to the third row if you want to. Maybe you want to do something, right? You can take the second row, you can divide everything by 2. You can add it to the fourth row. You can add it to the second row and create another set of values. You can do all of that, right? Those are row operations. And the thing about the simplex method, what it's really doing, and I'll mention this at the end of this video. I'm going to take a YouTube video where a gentleman is attempting. I don't think very many of you can follow that, right? He's attempting to show you where it's really taking the vortices, each vortices of the feasibility region, and putting it into a set of equations to bring out the maximum value of P, or the objective function, the maximum value of the objective function, or the minimum value, right? So it's the same thing, but it's just arithmetic. That may not seem to make sense unless you really know matrices and understand what's going on. And your aim really, most of the time, not all the time, is that you get like, okay, you get a matrix where you have maybe a 1 here, a 0 here, a 0 here, some other number here, a 0 here, a 1 here, a 0, and a set of numbers here. Remember this already? You start looking like the unit matrix. A 0 here, a 0 here, a 1 there, and some other things here. And at the end here, after you've done all these row operations to transform something like this into something like this, end here will actually give you the maximum or minimum value of the objective function, this last number here. And it will tell you maybe the X value, the Y value, or the Z value of at which the optimization function achieves its maximum or minimum. So it's really matrix. It's matrix. But remember, matrices kind of strip out all the words and all take out all the X and Y's, and so you just have numbers. So when you do the operation, it seems meaningless, but it's not. It's not. For those who have a deep understanding of matrices, will know that it all makes sense, right? However, I'm not requiring that of you. All you got to do is you got to see the problem, whether it's like a paragraph form or some table. You have to make your inequalities, uh, and then you have to follow this procedure, right? So let's start with a very simple after based on. So you know why I go to the next slide. All of this is blocking off my already. One second. But so these are some steps in order to um, do the simplex method. Well, in this case, it's a maximization problem, right? So you see them telling you, well, you convert the system of inequalities to equation, right? Using what I call slack variables, right? So notice mention is made here that we're okay. And you are used to okay, you know what inequalities look like. Right? So you will see what we call slack variables. Really, what we really mean is that we're going to replace the inequality sign. We're going to introduce a variable, right? All kinds of names you see they will call it. You know, I think this writer of this portion of thing is going to do something R, S, T, right? So when you introduce the slack variable, you'll see how we do that in just a minute. You set the objective function equal to 0. That's another step. You create something called a simplex table or tableau, right? I'll say table. And you label what we call active or basic variables, right? I'll in the next slide, I think, a couple of slides from now, you'll see what they mean by that, right? When we talk about active and basic variable, we'll say. Then there's something called, you see, like a pivot column. What's this pivot column? Well, it's a column with the most negative number on the left side of the bottom row, right? Again, you have to see the thing to know, right? You will see one just. So it says if all numbers on the bottom row are non-negative, then the simplex procedure has really run its course and you are done, right? Then it says to select the pivot row. So we got a pivot column already. And now we want to pick out the pivot row. How you will know that? How you will know what is the pivot row? Notice what it says. It says you divide each entry, right, in the constant column by the corresponding positive entry in the pivot column. Smallest positive ratio indicates the pivot row. You will see that demonstrated. Then it says select the pivot, which is the entry in the pivot column and pivot row. Right? Pivot must be positive. You hear that? Cannot be 0, has to be positive. Then what you do, you identify the new active variable. What is going to happen? A certain variable will take their exit and a new active variable come into play. Right? Start down there, sorry. More steps. Then I spoke about row operation. Right? Perform row operations to make the pivot equal to 1 and the remaining elements in the pivot column equal to 0. I just showed you something of that in the matrix, right? So you want to make the, I think this word is, should be making the pivot equal to 1 is optional. A word not pilot. If I made a mistake, right? But we can stay with, we want to make the pivot 1, right? And next they say repeat the same process, this whole process from 1 to 7 by identifying the most negative entry on the left side of the last row. And go again, right? So it said once the left side of the last row is all non-negative, the solution can now be formed. And the value of each row variable or active variable is equals to the rightmost entry name. All inactive variables equal 0. So all of this is almost given until you see an example, right? So let's take a real problem, right? But okay, before I go into the problem, um, here what is it? Active or basic variables correspond to columns that contain only one and non-zero entry, right? Only one and non-zero entry. And it says inactive or non-basic variables correspond to columns that don't contain only one and non-zero variables, right? And they're telling you to label things and so that you can track stuff, right? All of this is going to only make sense when you see the example. So that's so here you have that yellow dot. Don't be taken away with that. I don't know what's it. What is doing it? Yeah, some kind of pointer or something. Or something. So here you have some conditions, some constraints, and you have an objective function p, which you want to maximize, right? So basically, what you have to do is a 4-step says convert the system of inequalities to equations using slack variable, right? And then you set the objective function equal to 0. And then you create this table. So where did I get this table from? Where did I get this from? Right? Let's see. Let's see. So come here. Right? Notice what I did. So you got 2x plus y. And I add in something called a slack variable s. This is not 5. This is s. So 2x plus y plus 5. Sorry, plus s. I myself said equal to 5. So notice I'm replacing the inequality sign with an equal sign. So what takes up the slack? Remember, 2x plus y is less than or equal to 5. But by introducing s, you call it a slack variable in that if you add a certain number to 2x plus y, it's going to be equal to 5. So we call s a slack variable, right? You do the same with the second inequality, x plus 2y. We add a slack variable t, and then you make it equal 4. And for the p, the objective variable, take everything to the side of the p, right? And you will get minus 2x minus 5y plus p equals 0, right? Remember you said that? Set the objective function equal to 0, right? So I put the x and the y and so on this side because we want to line up all the x and the y's, and so we're trying to line up. But s and t, they can't line them up. They have to have their own column, right? So we do this here. So here is it. We are actually doing what these 3 steps, right? And we can fill in zeros here, right? Here you see the s, you can put plus 0, plus 0. You put in 0 here, and so, right? Put in 0 here, put in 0 here. So that's it, right? So we put in all the zeros and so. So now we take these coefficients and we put it inside of this table here, right? This particular writer actually labeled, sometimes, especially these here, S and T and P, sometimes people don't put any, right? Sometimes people don't put any. Sometimes you might watch some examples online and say, sorry, but I didn't do that. He put it in because it helps him. It helps the person track which variable is where, and which is going out and which is being replaced and all of that, right? So we got our table, right? And you can see it looking like a matrix, right? You're looking like a matrix already, right? Right. So our next step, uh, we want to find that pivot column, right? We want to find that pivot column. How we find it? Notice they say this is the column with the most negative number on the left side of the bottom row. Look at the bottom row. You see, the pivot column, you have -5. That's the most negative number, right? See that? Right. So now you want to know the pivot row. How do you know that? What do you do? Right? You take each of these values here, right? 5 and 4. You take these two numbers and divide them by these numbers, 1 and 2, right? And you get 5 and 2. Oh, and some textbooks, and so you'll see that they have an extra column here that call it ratio, right? Something you see here, don't say that. So we do that division and we find we get 5 and we get 2. And because this is the smallest, notice um, it says, let's get this. Select the pivot row. And how you do it is they tell you divide each entry in a constant column, that's this column here, the primary key, by the corresponding positive entry in the pivot column, right? So you take 5 divided by that 1, you get 5, 4 divided by you get 2, right? It says the smallest positive ratio indicates the pivot row. But this is the pivot row here because when you divide, 2 is the smallest. So where the pivot column coincides with the pivot row, that number 2. What we're going to do with this number 2 now? Well, we're going to do some further operation, right? We're going to take that 2, right? And this is what we're going to want to make it into a 1, right? And when we finish with doing that, we want to make, 1 second, I said, we want to make this 2 into a 1, right? And well, how do we do that? We divide the entire row by 2. And that's what I told you. You can do these things with matrices. These are called row operations, right? Right. What is our next step? We want to actually make this 1 into a 0, right? And so and you want to get rid of this 5 from here too as well. Right. So oh, by the way, so I told you you divide everything here by 2, and that's what they're telling you here. That this row is now going to become half of row 2, right? So take this and divide everything by 2, and you get this row, right? Get this row. So what do we do with this row and this row, right? Look at what happens. So the first row, I take row 1, that's this row here, and I minus it from row 2. I should say I'm subtracting row 2 from row 1, right? And this is what you get. You can check it. You can check it out, right? Take this row, subtract it from that, and you get this. So notice over this where the pivot value, right, was, you have a 0 there, and you want a 0 below here. So what do you do? Notice again. And here is where you ask me, so how do I know what to do? Well, here's where you have to use some common sense. I can't give you a rule, right? I can't give you a rule. You have to look, what can I do, right? To this row, you know, or we can, what can I do with 2 rows to make this row here into a row such that the number above this one is a 0, right? And you see what happened here. I took row 2 and I subtracted from row 1. You can do these things, right? So I took this row, subtracted from that row, right? And you can see if this is 1 and this is 1, subtracting this row from that will give you the 0. The last one, right? They say take row 3, right? Take row 3, that's this row here, this row here. Take this row. and add 5 times row 2. And the thing about row 2 is that row 2 has a 1 here, right? So if I multiply that by 5 and I add it to minus 5, you get a 0, right? And that is what we want here. But what we do to one element, we have to do it to everything, right? So that's what we need to do. We need to add row 3 to 5 times row 2, and you will get these numbers here, right? Good. So what has happened now? Have we reached the end, right? They tell you to repeat the process, right? Repeat the process by identifying the most negative entry in last year. But guess what? You see no negative here. So it means then that we are complete. We don't have to go more further, right? There are some times, as I said, when you have to continue the process, right? Where you got to make this 3 over 2 into 1 and so sort of more steps. But in this case, no. We have no negatives here, no negatives. Therefore, we're done, right? Remember, this was just a 2 unknown, if I should say that. There are only 2 unknowns, so you won't have to do plenty steps, right? Again, don't do this by hand. What are you doing this by hand for? How would you know this? By miracle? You might not know it because you're not experienced. It's not something you had done at CXC and maybe you had done a couple of courses in electricity and so, right? So with that, now we're done and we can now conclude, right? We can now conclude then that the maximum of P is 10, and it happens when S is 3, Y is 2, T is 0, and X is 0. Right? So these are the variables. S is 3, Y is 2. Right? Those are the 2 conditions. T is 0, X is 0. Right? And I think that would give you a max. Right? See, yes, I think if you were to use, yeah. Okay. 0, where is that? X is 0, Y is 2. Yes. At this point, at this thing here, why not 2, 2, 1? 2, 2 times 2 is 4. 4 plus 5 times 1. 5 times, that's 9. Times 9. But notice where when we use this point here, 0, 2. X is 0 and Y is, we have 10. That seems to be the maximum value. Yeah. It's strange, like I've never seen when you use one of the coordinates of 0, you do have a maximum. You always, I think all the examples we did during the tutorial last week, it's always this value here, right? It's like a node where X and Y has some value other than 0. Well, you see, the more you live, the more you learn. Right, so I'm going to pause the video a little because I want to go to another set of examples. Another example, in fact. But in this example, we're going to deal with 3 unknowns. Things are going to get very hard, right? Going to get very hard. And I hope you can keep up. But as I said, I mean, this one was easy. But the others will not. The one when you have 3 unknowns is going to get very complicated, right? So let me pause the video a little in a second. What's happening to my control? Good. So yeah, I just had to go and grab these slides from another writer, right? So again, here is some steps again that we use to, you know, we use to execute the simplex algorithm, so that we can get our maximum or minimum value for our objective function, right? Uh, Most of the books, you will see them always highlighting maximum values. There's a little one at the example at the end where we did some minimization, right? Um, and those they get a little more complicated and so, right? Remember, we only have a certain limited amount of time. We need to do a whole course and something like this to really get it, right? But yeah, the same steps almost as the last guide, right? I'm going to do the same procedure, no difference really. If you want to pause the video, as the thing says there, pause it and study the step, right? It's the exact thing that the other guy said, but remember, this problem now, we're going to have three unknowns, so things are going to get a little complicated, right? Right. So let me go back to, so yeah, so this is a problem, right? So we have a objective function P. We have some constraints. And notice we got X, we got Y, and we got Z and these, right? We got three unknowns. So, well, I think the last example, we actually introduced something called slack variables, right? R, S, and T are used this time. I think the last one was R and S only, right? Well, here now we have R, S, and T, right? So we introduce them, we get rid of all our inequality signs, and we now have equal signs. We're going to take these now, and we are going to make up our force table, right? We make up our force table. And that's what the table looks like, right? I think this writer, he threw in this R1, R2, R3, R4 to kind of keep track of the rows, right? And I think in the following tables, he's not using the same R1, R2, R3, R4. He's going to name it R5, R6, R7, R8, just not to confuse. You got the last one. You had a new R1, a new R2, a new R3, and so on. And it could be confusing to some people, right? But so we got all this information. Notice what they did. They just use all the coefficients, right? Like P here, you use what? -3, -4, -5, right? And the rest are zeros, right? He set up his thing a little differently. 2x plus y plus r equal 10. That's this row here. The slack variable r, right? So there's no s inside, there's no t. So then the second one, that's what you see here. There's no x. There's 2y, yes. 1z. No r, right? There's one s, no t, right? And all of that equal to 20, right? And so on. But so what we do now, we got to identify our pivot column and all of that, right? So that's what we're doing now. So we look for the column using this bottom row as a gauge, right? Where do we see the smallest negative number, or the most negative number, right? You see the zero, right? The Z column, sorry, the Z column. Good. So what we do now, we take each value here, 10, 20, 30, and so divide by the 0, the 1, the 2, or the 5, the -5, right? You divide by these three numbers. So you divide these numbers Like these numbers, and you get it there, right? The one with the lowest ratio is the 15. So this then becomes your pivot row now. What will happen is that when you do that, on your next table, you're gonna kind of shock out T. You're gonna replace it with Z, right? Replace it with Z, right? This variable is going to be exiting from the whole calculation, and Z is going to take its place, and that's what we see here, right? So we identify our pivot column and so on and row, and the number here too, right? What we're going to do? We divide everything here in this row. Notice, uh, this Z now come down here, right? Remember that. We take this row, we divide everything by 2. Everything by 2, right? And let's fill up this table and see what happens. All right, so you divide everything by 2. So that what happens to the 2 now? The 2 becomes 1, right? And you do the same to everything. Divide everything by 2, right? That's what you're saying. Row 7 is equals to row 3 divided by 2, right? So you take this third row, divide everything by 2, and you get it. Right? What do we do for these other rows now? Because remember what we want is that above here, we want 0, right? And below here, we want 0s, right? So I know it's a big leap, right? It's a big leap. So look at what happens. Row 5, you simply take row 1 and put it back there because they already get a 0 here, right? Already get a 0, you gotta worry about that, right? This row now, how do you arrive at this row? So this row is equals to row 2 minus row 7, right? So you take row 2, this row here, take this row, and you minus this row 7, right? Now you see there's a 1 there. So if I minus this 1, you'll get a 0, right? And that's what you want. You do it for all the other elements, and you get this, right? And this one at the bottom here, what do you do? Notice you take row 4, that's this row, plus 5 times row 7. So you take the same row here, right? Multiply it by 5 and add it to this row here, and you will get this. And the desired result is that where this 1 is, you got 0 above and 0 below, right? There's that thing in row operations in matrices that you got to get used to, right? So you're repeating the same procedure, not doing anything different. You're repeating the same procedure by looking at this row here, and you see there's a -4, right? So that becomes your new pivot column, right? And that's what's happening here. So this row here is your new pivot column, right? 1 second. So again, what you do, you take these numbers at the end here, and you divide by all these numbers, the 1, the 2, the 0, and the minus. Well, no, don't divide by the minus. You do the divide by 1, divide by 2, divide by 0. And which one has the lowest ratio here? It's this one here, right? 5/2. Now that then gives you this pivot number here, right? See? So this now tells you that well, what's going to happen is that Y will now take the place of S here, right? And that's what you see in our new table, right? So Y goes in. You see what we're doing? We're systematically getting rid of the slack variables. We got rid of, what was it before? I think it was T. Now we got rid of S, and you know the next step is going to be to get rid of R. Anyway, good. So we got our this column here, make it into a 1, right? And remember what we want to do now. We want to make this into a 0, that into a zero, that into a zero, right? In other words, I want to make this into a zero. So this is already a zero. I didn't do nothing to that. And then, well, you don't have to worry about this. Yeah, you have to change that into a zero as well. How to do that? Well, the procedure is here. Look here, right? All the row operations are spelled out here. You take your time and see what happens so that we can get these zeros, a zero up there, zero here, zero here, right? And when you're finished doing all of that, you repeat the same procedure. You see that, oh, there's still a negative number here. So this is your pivot row, right? Right? So you take all these values here and you divide by these, and mind you, that's going to be hard work now because you're dealing with fractions, right? And you do that division, you see, well, okay, you get 10 over 3, you get minus 10, and you get 30, right? And I think, what is it, 10 over 3? Don't worry with the minus sign, right? You're using the number 10 over 3, which is the smallest number. I use the magnitude, by the way, right? Use the magnitude. So this is the smallest ratio. So then this becomes your pivot row now. You got your pivot column, you got a pivot row. So you take this number now, you want to make that into a 1 by doing what? By dividing everything by 9 over 4, and that's another craziness. Oh, by the way, now your x is going to replace the r, right? So you get x here. And now you have to now get zeros below here. How? Notice the suggested row operations that will do that, right? You take your time. You got a whole week to see what they did to get the zeros below there, right? And when you finish doing all of that now, well, because there are no negatives here, the process is complete, right? And really and truly, this is your maximum value, the 90. And it occurs when x is 10 over 3, y is 10 over 3, z is 40, right? And if we were to use those numbers and we put it inside the objective function, we'll see that, yeah, they satisfy the constraints and at the same time maximize the objective function. Right? So I know it's a complicated process, but remember what I said at the beginning? Get a simplex calculator, and during the tutorial, I'll show you a couple of them. I'll actually use them. Who's going to do this by hand? Me? I must be crazy, right? And so I know you'll have to pause this video a lot and watch the operations one by one. Right? That's your job. You have to spend time with it and see what was being done. As I told you, if you have a good simplex calculator, you don't have to do none of this. You just have to form your inequalities, right? Some calculators, you have to make up the table. Some you don't. They just want to see the inequalities and they will do it for you. This is a minimization example, right? So here it is. You have an objective function, p equal minus 2x plus 3y. And you have some constraints, right? So I think this one only has x and y inside. So they actually just use two unknowns because they don't want to use a complicated example. They want to bring out when you're dealing with minimization function, what you have to do with your objective function. Notice what is done here. We let q be equal to minus p, right? So we kind of put in a minus sign there. We get this equation, which we're going to put in our table, right? We're going to put in our table. And when we go through the process, right, we're going to get the The maximum value is minus 3 over 2, sorry, 32 over 7, and it occurs when R is this and X is this, right? So when R is that, really you mean Y is 0, right? Y is 0. And you won't use the positive, you use the negative, because remember, P is equals to minus Q, right? So we kind of jumped the steps. We didn't show how we got all of this. But I just wanted to show you that when you deal with minimization, how sometimes you have to redefine P, right? And when you get the answer for Q, you just minus it, right? Take the minus of it. And that's going to be your minimum value. Right, so I'm going to add on a little explanation. It's very difficult for you to follow, but there's a guy on YouTube who tried to explain what is this process of simplex really? What are we doing with these matrices when we're trying to get all those ones and zeros? What are we trying to do, right? And you'll see he will try to explain that, what this thing really does is that you are actually traveling around the feasibility region, and you are making at one time X equal to a certain number, while the rest Y and so is another number, 0 or so, and you travel around until you get a maximum value for P, and in other cases minimum, right? I'm going to attach it to the video at the end, as well as yeah. Well, during the tutorial, we'll actually use some calculators to do it, right? So you'll see some more examples there where we have a calculator doing the job for us. Good, so yeah.
Okay, well, in this video, Mark and I are going to discuss the simplex method, which you read about in section 7.4. We're not going to go through the tableaus and the treatment that you saw in 7.4. Rather, we are going to try to give you a conceptual sense for what is going on in the simplex method. So, just to remind you, the problem is to maximize a function. In this case, it was a function of two variables, subject to some constraints. Now, this is the carpenter's problem, just to remind you. The initial constraints were inequalities, but through the introduction of slack variables, these have been converted into equality constraints. If you're still confused about slack variables, we will try to clarify those in the future, but I will indicate what they do for you geometrically in just a second. So those are our two constraints. And
John, just to stop you, we have a couple of the constraints too, which it looks like you're writing down right now.
Yes.
So I'll shut my mouth.
Yes, so we're looking for everything to be non-negative. Okay, we've already seen in the reading a geometrical interpretation. And just to sketch it quickly, there was a feasible region. I'll just label everything in just a second. Feasible region is in the shaded area. And what I've drawn here are the lines that correspond to each of these constraints right here and here, right? So we have this, for example, which we might often label x1, but in fact this corresponds to x2 equal to 0. So we know we're looking for solutions in this region because x2 is positive, and we're not looking for solutions down here. This, which we often call the x2 axis, well, that's really just x1 equal to 0, and we're looking for solutions over in that quadrant, right? Because over here x1 is negative. Likewise, this is the y1 equal to 0 line, and it may not be obvious from that equation, but since you've already seen this in the reading, y1 is positive if you're below that line and negative on the other side. And this is y2 equal to 0. And likewise, y2 is positive if you're below that line. Okay, so that gives us the feasible region. We know from the theorem that we read about that the optimum is going to be at an intersection point. Okay, so simplex method. And here we think about the simplex method conceptually. So initially, we want to maximize our function 25x1 plus 30x2. I'm going to assume that we already have a feasible point, and here we're going to take our first intersection point, which is 0, 0. Okay? And we know that the value of the function there is 0. And now the question is, can we do better by moving along the perimeter? Okay, we already know there's no point moving on the inside. We can just move along the perimeter. So when we ask that question, can we move along the perimeter and find a larger value, there's two options. We can either go this way or that way. Right? Now notice, if we move this way, when we move this way, when we move along this line segment, x2 equals 0. So we could ask the question, should we keep x2 equal to 0? Or if we move up this way, we could ask, should we keep x1 equal to 0 and increase x2? Okay, well, we clearly have a choice. Which way do we move? Well, first of all, is the value of the function going to increase? A quick inspection of the function tells you that, yeah, it's going to increase in both directions because increasing x1 or x2 increases that function. So we have a choice to make, and that is we choose the direction of fastest, if you like, fastest increase. Okay? So how do I know what that direction is? Right? Well, if I keep x2 equal to 0, my objective function just is 25x1. So we know just from calculus that that has a rate of change of 25 or a slope of 25. So as I increase x1 by 1 unit, the objective function increases by 25. Likewise, for the other case, if I increase x2 by 1 unit, that slope in that direction is 30, so it increases at a higher rate than the other direction. So here we should keep x1 equal to 0, and we should increase x2.
So I want to just clarify something you said, John, that I think is important, which is you could look at this and you could say, okay, I'm going to compare how big the objective function is at this point and how big the objective function is at this point. I'm going to choose the one that's got the bigger value. And you're not saying that. You're actually saying you want to walk in whichever. You could either walk in this direction or you could walk in this direction. You want to walk in the direction that's where you're going uphill the fastest, right? That's steepest. And in this case, walking in this direction where x1 is equal to 0 but x2 is increasing is the sort of faster direction to go uphill.
That is right. Although it's no guarantee that by the time you get to the intersection point, you are higher than you would have been by going the other direction. It's just that you initially start walking uphill faster. In fact, you keep going uphill faster, but now the question is, how far do you go? So absolutely, it's a local argument about starting right here. Okay, so we keep x1 equal to 0, we increase x2. How much can we increase x2? This, I think, is where the geometrical picture is quite nice. We keep increasing x2, right, as much as we can. But, if you like, we don't want to violate a constraint. Right, so for example, if I increase x2, as I hit this intersection point, y1 has been positive the whole time, and y1 just became 0. If I keep increasing x2, y1 becomes negative, which in life is fine, but if I want to satisfy these constraints, I'm going to disallow. So I'm just not going to allow us to move beyond that point.
So you just walk in that direction until you hit the first intersection.
I walk until I hit the first intersection. Okay.
Once you've hit an intersection, then if you go past that, you violated the constraint.
Exactly. So in this case, we go until y1 equals 0. And if I'd had a different picture, it might have been y2 equals 0. Who knows? Okay, so now we're at this intersection point. And now we need to understand the landscape around us. And when I say the landscape, I sort of mean, what's the coordinates that we're using here, and what directions can we move? Okay? So now that I'm at this point, let me just label this as A, and I'll write this as A. Now let's say we're at point B. Okay, and you can see that maybe this example in 2 dimensions is not nearly as useful as it might be in higher dimensions, because if we play this game, we don't seem to have many options. Okay, but I'll pretend that we do. Sitting at this point, we could move in 2 directions. We could move so we could maintain, what did I say last time? We could keep y1 equal to 0, right? Or we could keep x1 equal to 0. Okay, so I'm thinking about x1 and y1 as now being my coordinate axes, if you like. Okay.
And so keeping one of those equal to 0 just means that you're moving, by keeping one of those variables, slack variables or decision variables 0, you're forcing yourself to be on the boundary somewhere.
Exactly. I'm forcing myself to be on the boundary. Now, the reason I say this may seem artificial is, great, I can imagine why I might want to keep y1 0, because that means I can walk along this line. Keeping x1 0 means I keep walking along this line, but I've already ruled out going any further, and there's no point going back. Okay. But in higher dimensions, and maybe we'll comment on that in a minute, there's going to be more choices here. Okay, so now I keep y1 equal to 0, or I keep x1 equal to 0. I need to ask the question. Choose, again, the direction of fastest increase. Okay. Now notice this implies something, because when we initially wrote our objective function, I'll just write it as value, we need to express this as a function of x1 and y1, right? Because as I vary x1 and y1, I want to know in which one leads to fastest increase. So that's connecting back to the reading. That's why we take our initial expression, which was in terms of x1 and x2, and we use one of the constraints to re-express x2 in terms of x1 and y1, so that we have a new expression in terms of x1 and y1. And I'm not going to do the details here, but that's why you're doing that. So you're really rewriting or making a variable transformation, and we did that quite a bit in linearity 1. We're transforming our coordinate system, if you like. Okay? So we do the same thing. We figure out which direction. In this case, it's keep y1 equal to 0. And move, okay? And you can see that we move in this direction. And generally, a couple of things could happen. As we move, we may start to approach an intersection point where we're about to violate a constraint. In this case, we approach the intersection point where y2 becomes 0, okay? And again, we don't move past that point because we don't want to violate the constraint. So now we're sitting at point C. Right? So at point C, we have y1 equal to 0, and we have y2 equal to 0. And now if I think about that as my key coordinates, I'm going to move along one of those axes. So I'm either going to keep y1 equal to 0 or y2 equal to 0, but we can see geometrically that there's nowhere left to move. Right? If I move along y2 equal to 0, I'm going to decrease. Mm-hmm. And we would see that by, again, expressing the value as a function of y1 and y2. And when we do that, we see that whatever we do to y1 and y2, in terms of increasing those values, the function value is going to decrease, and we know we're done.
So I guess maybe a question that I think we could ask people to think about at this point, and we're not going to answer in this video, is sort of, okay, we've walked through this sort of qualitative explanation of what's going on in the simplex method. Which of the steps of the simplex method correspond to each of these decisions? Like, at which point do you actually decide that you've got an intersection? At which point do you figure out what the direction is of greatest change? How do those steps in that algorithm correspond with this sort of qualitative picture? And if you can look at that algorithm and understand how these qualitative steps correspond to the algorithm, then you've really got this under control.
And what a great topic for Thursday that would be.
Indeed.